There we go. Oh, can everyone still hear me? My computer the screen just went completely black, except for a spinning wheel. Oh, great, you're back. Okay, so that's Clairaut's theorem, and that's the main application of multidimensional derivatives that you're going to need to know. Okay, the other thing that you're going to want to be able to do. Oh, so I have a question. The question is, which derivative did I take first? So I started out with a question that asked me to take the derivative of x first and then the derivative of y. But instead, if you want to take the derivative of this with respect to x, then you have a mess because you end up needing to use product rule. Whereas if you just flip them around, and take the y derivative first, then there's no y dependency. So you just immediately get a 0, okay? And remember, when you take these derivatives, it's the same as functional composition, right? Like if you take f composed with g of x, this is the same as f of g of x. And it's the same with derivatives. Whichever one's on the right, you apply that one first, okay? So I think these are the two major topics that you have to know about at least the last 2 weeks, or last 2 or 3 weeks. So the topic for this week, did he say in class whether this week is going to be on the midterm? Oh, so you don't have to know gradients at all. No gradients, okay. Oh, okay, so I forgot one topic. So the other topic that you're probably going to have to know is you should know how to sketch level curves, okay? I think that's important. And in terms of sketching level curves, the only thing that you have to do is if you get some sort of function f of x, y, hopefully he won't make you do a 3-dimensional one on the exam. But if you get some function f of y is equal to something, or just a function like this, then what you want to do is you want to set f of x, y equal to constants. Just set it equal to various constants and think about geometrically what you get out. Okay, so a good example is just the circle. If you have x squared plus y squared is your function of x and y, then just set this equal to several values of c, and you'll see that you end up getting circles of radius root c. Okay, so that's how you sketch level curves. All right, so those are the main topics that I can think of. So can anyone think of anything else that I might have missed that they'd like me to talk about? How detailed or exact do those level curves have to be? Oh, that's true, arc length and curvature. Okay, so yeah, I can say something about that. Right, okay, so okay, first, in terms of how detailed the level curves have to be, I don't think they have to be very detailed. Like if you just drew this for this function, I think I can't say for certain because I don't know which questions I'll be grading, but I would say that this would be fine with me. I don't think you have to label, oh, this is the level curve of 1 or something, or I don't think you have to do any of that. As long as it's detailed enough that generally the shape of the curve convinces the grader that you know what you're doing, that's probably fine. But if you lose points, don't come and sue me or something, because I'm not 100% sure. Okay. Right, so in terms of curvature, how do you spell it? Curvature. Hopefully that's right. Curvature and arc length. I don't know how much I can say about these. With curvature, just know the formula, okay? I don't know if I even remember it off the top of my head. Maybe it's, well, I don't want to guess and confuse you, but okay, maybe I'll guess. I think it's like r prime times r double prime over what is it? Magnitude of r prime? Yeah, I think it's something like this. So look back, remember the formula for curvature, okay? Because I don't think that he's going to ask you to do much more than this. And one thing that you should remember about the curvature is just essentially what it means, right? Like we talked about this before, but the magnitude of the cross product of two vectors gives you the area of the parallelepiped that they span, okay? Or the parallelogram in 2 dimensions, okay? And so what you should think about is when you take a cross product of 2 vectors, in order to maximize the area of this thing that they span, this plane that they span, what you want to do is you want to make sure that these 2 vectors are as orthogonal as possible, right? Because if you have a right angle here, then then this area is going to be maximized. So then your curvature is going to be maximized. And likewise for your arc length, I think it's unlikely that you'll get anything trickier than just, do you remember the formula for the arc length, okay? And the formula, I think it's something like, it's the same as it would be in the 2-dimensional case or the 1-dimensional case, which you covered in single variable calculus. So if you have some curve that's parameterized as r is equal to, you know, r1, r2, r3 in terms of t, then all you have to do is you just take the derivative of each component with respect to t. Let me write it like this for convenience. And then you're going to want to integrate that result, okay, but between the 2 points of t that you're interested in to parameterize the curve. And I guess the other thing that you might want to know that seems important is when you have some sort of function, it seems like there were a lot of questions where he asked you to parameterize in terms of arc length. And when he asks you to parameterize in terms of arc length, all you're doing is you compute the arc length, and then you basically take your you take your function and you just divide out by the arc length between the 2 points, okay? Because you're trying to make it so that along the arc of the curve, by the time you go from one part to the other, instead of having like t run from 0 to 100 or something, you just want the arc length to run from 0 to 1, because you're trying to just move along that arc length, okay? So does this make sense to everyone? Okay, great. Any other topics that I should mention that you can think of? Oh, linearization. Something else. Linearization in this class. Linearization. Right, okay, so this is where you want to do an approximation, right? You do an approximation at a point that's close to a known point. So I think that there is a good example of something that is related to linearization and approximation of other values on this week's worksheet. But I guess one thing that I can say about it, aside from that, which does use the gradient, is that when you do linearization, what are you doing? So you have some sort of function that is, generally speaking, difficult to compute the value of. Okay, so say something like I don't know, x squared plus y squared. Okay, so this function at a random point, if you pick an arbitrary point, it's going to be difficult to compute, because say that I pick something like x is equal to 1 and y is equal to 3 or something. So then I get root 10. Okay, we don't really know how to give any numerical approximation for that. Well, I guess you do using Taylor series, but so the idea behind linearization is that instead of trying to compute this point directly, or let me, yeah, that's a good point. So instead of trying to compute this point directly, what you're going to want to do is you're going to want to compute a nearby point that you can easily get the answer for, right? Like, I think usually you want it to be closer than I can give you a point for, but say the point, I'm trying to get a 9 here, so maybe, yeah, okay, how about 3 and 0 or something? So then if you try plugging in 0 and 3 for the values here, then you easily just get back out a 3, right? But we want to get the value of the point at 1, 3, not 0, 3. And so then what we do is we take the value of the function at 0, 3, which we know, and then we're just going to want to move along the x direction from 0 to 1, right? So then we're going to want to take d dx of f of 0, 3, and then we're going to want to, in this case, multiply that by 1, because we're going to want to move from 0 to 1 in the x direction. Okay, and you can imagine something similar when you're doing when you want to move in 2 variables, right? So maybe if you have a point here that you know easily and you have another point here, then in order to approximate this point, you compute the value of this point, and then you maybe move along the x direction, df dx, and add, say this is a distance d1, so you might want to add this to your function, and then you might want to move up in this direction. And if you can easily compute the y derivative at this point, then that's great. And if you can't, then you just go back here and compute the y derivative as well, and then add that value going up. Okay, so times a distance d2, so maybe df dx times dy times d2. Okay, so does this seem okay? Is everyone happy with this? Comment? Yeah, but these approximation things are tricky. Sometimes you just have to do what makes sense, right? It's not always easy to compute at different points. So you just want to compute things at the closest point where you can, and then approximate from there. All right. Other topics that people want me to try and say something about. Okay. I think if it's all right with people and there are no more midterm questions, if there are midterm questions, ask now, because that's more important. but otherwise I'm going to start talking about the gradient and what you should know there. So last call, other questions? Other questions about the midterm? All right, then let me talk about the gradient. Okay. So, all right, the gradient I think is the most useful thing that you're going to learn in this class. The gradient is actually very important, and it's used in real life, not just in calculus, in many different capacities. And that includes machine learning and physics and probably even economics a little bit. I don't know much about economics, but so here's the idea behind the gradient. The gradient of f in 3 dimensions is just df, dx, df, dy, df, dz, okay? And what does this give you? So what the gradient gives you is, let's say that we're just dealing with a 2-dimensional function. And because I can't draw it if we deal with a function in 3 variables. So what the gradient is telling you is, if you take the gradient here, it's going to return on the plane. So if we go down here, it's going to return this, okay? Because this is the direction of the greatest increase in the value of the function, all right? And the reason this is used in real life is because when you're doing optimization problems, you'll have some sort of crazy function, and this function you'll want to minimize it, because minimizing this function will mean that you can approximate some other phenomenon very well. It's called a loss function. And so then when you're minimizing this function, what you'll do is you'll compute the gradient at a point, and then you'll move along the plane in the direction of the negative gradient. And the reason you're moving in the direction of the negative gradient is because it stands to reason that if gradient of f is the direction of the greatest increase, the negative gradient of f is going to be the direction of the greatest increase, okay? And this might not be true on a general function if you think about it, because logically this doesn't necessarily just intuitively follow, right? Like if you're taking a gradient here and for some reason your function increases most in this direction, it's going to decrease most in this direction, right? But the reason that this works is because infinitesimally, all of these surfaces look like their own tangent plane, okay? And so when we're looking at a plane, this is true. Like if you just draw a plane in space, if this is the direction of the greatest increase, then this is just going to be the direction of the greatest decrease, because we are dealing with a plane instead of some curved function. And when you get close enough to any of these smooth functions, they look like planes, right? Roughly speaking, that's the intuition. Okay, so where else do we see gradients and why are they useful? So another place that we see gradients is when we're computing these tangent planes, okay? So if we have some sort of function like this, and we take a gradient here, then I believe all of the vectors that are orthogonal to the gradient are going to form the tangent plane, okay? Does that make sense? So the tangent plane is orthogonal to the gradient. And why do we care about the tangent plane? It's again one of these linearization things. So if we compute the tangent plane at some point, and we know the value of the function over here, then if we want the value of the function at some other point that's nearby, then what we can do is, okay, it's hard to compute the value of the function at that point, but we can approximate it by computing the value of, say, the z coordinate of the tangent plane at this nearby point, because we're saying that z is equal to f of xy. And so if we find the tangent plane here, and we move along the tangent plane until we get to here, then we know that the tangent plane, at least in a neighborhood of this point, is going to be a great approximator of the function. And so that means that whatever the z coordinate of this point is going to be a close approximation for the value of the function at this point, okay? So is everyone following? No affirmation. Great, okay, one piece of affirmation. Okay, so let's get out the worksheet. And we don't have time for very many worksheet problems, but maybe I'll try and give you the highlights. So let's talk about exercise 1A. Let's try and do exercise 1A using the method that I've described here for approximating functions. So give me F's in the chat when you're done, or C's when you're confused. Okay, is there wide? Also, if you don't want to compute the whole thing out, that's fine. I know that the calculation gets a little bit unpleasant. So if you just get to an expression where all you have to do is rearrange some things, then that's fine. Ruh-roh. Guess we have 1C. Are other people also confused? I think we probably have many people. Yep, there we go. I'm getting the C's and the DMs. So if you sent a C, you're not alone. All right. So any Fs? Do people want more time, or should I go over it? I have a pretty good number of C's. Okay, yeah, more C's. So let me say something about this. The first step, as you may have imagined, is computing the gradient. So the gradient of z, which is our function, is 2x over 2 root x squared plus y squared. And if you're unsure about how I did that calculation, you should do it in the privacy of your own home, because there's a high chance you'll see something like it on your exam tomorrow. And then you get 2y over 2 root x squared plus y squared for your other derivative. And we can simplify. That's x over root x squared plus y squared, and y over x squared plus y squared. And we plug in the 0.5, 12, 13. Of course, we don't have to plug in a z. Oh, sorry. So also the derivative with respect to z, because z is just the function, if you like. This is just going to be 1. So you can include that if you want, but I guess it's not strictly necessary, or -1, sorry, because you can rewrite this as 0 is equal to x squared plus y squared minus z squared or something. And so then, minus z, not z squared. And then if you take the derivative with respect to z, you get a -1, okay? So then what plane does this result in? So we plug in 5 and 12 for x and y, and we get 5 over, so 5 squared plus 12 squared is 13, and 12 over 5 squared plus 12 squared root, that's 13, and then you get a -1, okay? And so then your tangent plane is going to look like 5 over 13 times x minus 5 plus 12 over 13 times y minus 12 plus z minus 13 times -1. And all of that's equal to 0. Why? Because if you plug in 5, 12, and 13 at the point where you took the gradient, you get 0, okay? And so now what we have is we have this function that maybe looks like this. And we took a derivative, or we took the gradient over here and computed the tangent plane. And so now what we want to do is we just want to compute the value of the tangent plane z coordinate somewhere over here that allows us to approximate this value of 4.98 squared plus 12.01 squared. And all we have to do is we plug in the points that we're interested in. So we do 5 over 13 times 4.98, minus 5, plus 12 over 13 times, so 12.01 minus 12, and then minus z minus 13. Sorry about the handwriting, is equal to 0. And now all you have to do is just solve for z, okay? And you get the value of the z coordinate along the plane at this new point, okay? So I won't do that part. Does that make sense to everyone? Cool. Let's see. The other, well, okay, I still have 6 minutes. All right, so I think the last problem that I want to talk about, okay, so is there anyone who has homework or midterm questions that they want me to answer after? Because, yeah, sure, someone says they have to go. So if anyone has additional questions, I can just stop now and we can talk about any more midterm problems. Because that might be more useful too, I think. We can deal with this later. Yeah, okay, so I think what I'll do then is I'll call it here, since I only have about 5 minutes left, and then anyone who has extra questions or topics they'd like further clarification on, you can just stick around and ask, okay? So if you have nothing else, then good luck tomorrow. and hope I'll see you next week.